Okay, so good afternoon in Japan, in Taiwan. And today is my great pleasure to have Professor Toru Kan from Osaka Metropolitan University. And he's going to share with us his result on boundedness of global solution of a superlinear heat equation. And we are very curious about his research. So let's welcome him.
Yeah, thank you for the introduction. I would like to thank all the organizers, especially Professor Dai, for giving me a chance to speak in NCTS webinar on nonlinear evolutionary dynamics. So in this talk, I'd like to speak about my recent result on superlinear heat equation. So this is joint work with Professor Yohei Fujishima in Shizuoka University. Okay. Oops. I write something, but can you see?
Yes, I see you are loading a page. Yeah.
Really? But
Yeah.
I cannot see my my handwriting. Can you see this
Yes.
red curve?
Yes. Yes.
Okay. Okay, so let me start with explaining our motivation. Okay, I use this iPad as a blackboard.
Very good. Yeah, we see introduction. So very smoothly. Good.
Okay. Okay, in this talk, we consider initial boundary value problem for superlinear heat equations. So the equation is given as follows. So time derivative of u is equal to Laplacian of u plus f of u. Okay, I think I'm given 1 hour and a half, but I think I just need 1 hour plus something.
Sure, no problem. We will interrupt you. In the end, you will be 90 minutes.
Okay. Okay, so we consider this problem in a unit ball. And on the boundary, we impose the Dirichlet boundary condition. And we write u naught for initial function. And we call this initial boundary value problem P. Okay, as I said, B is a unit ball. Sorry. In Rn. And we always assume that the space dimension capital N is bigger than or equal to 3. And for the nonlinear term, we assume that the nonlinear term is of class C1 alpha, positive for U positive, and superlinear in the sense that the integral of 1 over f is finite near infinity. And for
Toru,
initial...
can I interrupt here? Can I interrupt here? Hello? Can I ask a question?
Yes.
So you assume the dimension, space dimension is bigger equal than 3. Of course, there's a natural question. Why 1 and 2 are out? Oh, they are well known.
Yes, two-dimensional. So one-dimensional case is kind of easy to conclude the same as no. I think one-dimensional case is fine, but two-dimensional case is very exceptional. The two-dimensional case is the most difficult. So
I see it's open.
That's a kind of future work.
Okay, good. Thank you.
Okay. Okay, so I should say that the initial function is assumed to be radially symmetric because of some technical reason. And it is also assumed to be non-negative not identically equal to 0, and bounded. Okay, by the assumption that the initial function is radially symmetric, implies that the corresponding solution is also the radially symmetric. We consider only in radial setting. And also the positivity of the nonlinear term and non-negativity of the initial condition show that the corresponding solution is positive if x is in the ball and t is positive. Okay, we only consider positive solutions. Okay, we consider this problem, and let me explain what question we consider. So to explain what we would like to do, let's first consider an ordinary differential equation obtained by neglecting the diffusion term. Okay, let's consider this ODE. So as an example, we take u squared as a nonlinear term, and we write alpha for the initial data. Then you can easily solve this problem. If alpha is 0, then the corresponding solution is, of course, identically equal to 0. While if alpha is positive, then the solution is given by 1 over alpha minus t. This solution, you easily see that this solution diverges as t goes to 1 over alpha, which is finite. Okay, in this example, you have two alternatives. One is that you have the solution exists globally and is uniformly bounded. Otherwise, the solution blows up in finite time. Okay, if you replace the right-hand side by u, then the corresponding solution is given by alpha times e to t. This exists globally, but is unbounded. But in this case, there's no such solution. So in this case, we don't have any unbounded global solution. Any unbounded solution?
I have a
Yes.
remark.
Yes.
In my community, we call global bounded solution. Okay, I mean, we call blow up solution or grow up solution.
Yes, grow up solution. Yes.
Grow up solution is unbounded global solution. Okay.
Yes, in someone said so blow up in infinite time or something for
I think grow up is but okay, I see.
It
Yeah,
depends
just for
on
your
people.
reference. Yeah.
Okay.
Very good.
Thanks.
I see.
Yeah,
Thank you.
Thanks for your attention. Okay. Anyway, so this means that once you once you know that the solution exists globally, then the solution must be bounded in this case. So it is natural to ask the same is true or not for our PD. So the question here is any global solution u of xt of p uniformly bounded? This is a question in this talk. Yeah, this question is actually quite important because once you know the uniform boundedness of global solution, then you can find that the omega limit set of solution consists only of stationary solutions. That's very important. That's very useful information to examine the asymptotic behavior solutions. So this is very important question. Okay, so we consider this is true or not. So the answer changes depending on the growth rate of nonlinear term. Okay, let me explain some known results. Okay, first we consider the case that the nonlinear term behaves like some constant times u to the power p with a positive constant lambda and the exponent p bigger than 1. Precisely speaking, this symbol means that the limit of the ratio between f of u and u to p as u goes to infinity is equal to the constant lambda. Okay, if p is less than the Sobolev exponent, ps, which is defined by n plus 2 over n minus 2, in this case, the answer of this question is yes. So all global solutions are uniformly bounded. So there are so many results for this case, but I just introduced. So I just introduced some two of them. This was shown by Kaznav and Lyons in 1984, and in the same year, proved by Ni, Sachs, and Tavansis. Okay, let's move on to the case that P is equal to PS, the supercritical case. Now, this case is quite exceptional. In this case, the answer is no. There's some unbounded global solution. This is shown by Ni, Sachs, Tavansis. This is the same paper as this. And, sorry, Galaktinov. And Vasquez.
Toru, I have a question here.
Yes.
So, do they also consider bounded domain or the whole space Rn?
Yes, you can also consider the whole space, but okay, so the result is a little bit different. So, okay, in subcritical case and supercritical case, the result is the answer is the same. Yeah, but yes, if P is large, then the result is a little bit different.
I see. And also for the critical exponent, do they also have a dichotomy, like either uniformly bounded solution or brought up solution?
Yes.
I know there exists, I mean, some initial condition that the solution is not uniformly bounded global, but whether the dichotomy holds.
Yes, it should be.
Okay.
I remember, but it should be. Yes.
Okay, interesting. Thank you.
Okay.
So,
Because this is this is a gradient system.
yes.
So okay, there's no so periodic solution. So the kind of so the solution behaves terribly. So there's no such solution.
Mhm.
Okay. Okay, and so okay, let's go to the supercritical case. In that case, the new exponent PJL, which is often called the Joseph-Lundgren exponent, plays an important role. This exponent is defined by infinity for the space dimension n less than or equal to 10, and by 1 plus 4 over n minus 4 minus 2 times square root of n minus 1 for the space dimension n bigger than or equal to 11. And if P is between the Sobolev exponent and the Joseph-Lundgren exponent, then you have the uniform boundedness of global solutions. This was shown by Galaktinov and Vasquez. On the other hand, if P is beyond the Joseph-Lundgren exponent, then the answer becomes no. There's some unbounded global solution. This was shown by Lacey, Sanatis, and Perol, and Vasquez. I think in bounded domain case, so there's no result for the case that P is equal to PJL. So in unbounded domain case, there's some result for the critical case. Critical means that P is equal to PJL. But in bounded domain case, I think there's no result for the critical case in the sense of Joseph Lundgren. Okay, anyway, in the case that F behaves like U to P, then there are many results. Okay, let's move on to the case that the nonlinear term F behaves like some constant times the exponential function. Okay, as you see, if the space dimension is less than or equal to 10, and if f of u behaves like u to p, then you always have uniform boundedness for global solutions, because the Joseph Lundgren exponent is infinity in this case. So even if f of u grows exponentially, we have a chance to get uniform boundedness if the space dimension is small. In fact, it is known that if the space dimension is less than or equal to 9, then you have the uniform boundedness for global solutions. This is shown by Fila and Plotchik in 1999. While if the space dimension is larger than 9, then there's some unbounded global solution, which was shown by Lacey, Sanadis. Oops, I'm so sorry. I'm so sorry. I had a mistake that, so these references are not correct. This should be here. Okay, I rewrite. Okay, so this part was shown by Lacey and Sanitis and Pereira and Vasquez. But this case, this result was shown by other people. More precisely, this was shown by Dole, Galactinov, Lacey, and Vasquez. I'm so sorry. Okay, these are results. I know. So I introduced many results. So let's put all the results together in a table. Okay. Okay, I divide the cases according to whether the space dimension is less than 10, equal to 10, or bigger than 10. And for the nonlinear term, we have three cases. F behaves like some constant times u to p, with p less than the Joseph Lundgren exponent and is not equal to the Sobolev exponent. The Sobolev critical case is quite exceptional, so that may confuse you. So I just omit to consider the Sobolev critical case. Okay, the second case is that nonlinear term behaves similarly, but the exponent p is bigger than the Joseph Lundgren exponent. The final case is that the nonlinear term behaves like the exponential function. Okay, so since the Joseph Lundgren exponent is finite only if the space dimension bigger than or equal to 11, so we have to exclude these cases. Okay, in lower dimension, namely in the case that the space dimension less than 10, then we always have the uniform boundedness of global solution, even if the nonlinear term grows exponentially. On the other hand, if the space dimension is 10, we still have the uniform boundedness for f behaving like algebra polynomial, but we have unbounded global solution if the nonlinear term grows exponentially. In the case that the space dimension is higher, then even if the nonlinear term behaves algebraically, there's some unbounded global solution. Okay, this is a summary of the results I introduced. Okay, so basically, if growth rate of the nonlinearity gets larger, then we have a chance to get unbounded global solution. What if the space dimension is lower, then we always have the global boundedness, uniform boundedness. And in this talk, we focus on the lower dimensional case. More precisely, we consider what happens if the nonlinear term grows faster than the exponential function. We still have the uniform boundedness, or we may have unbounded global solution. So there are two possibilities. One is that there's some special nonlinearity. Let's say e to u to the power p, such that if the exponent p is less than some special exponent p star, then all global solutions are bounded. While if p is bigger than p star, then we can find unbounded global solutions. This is one story. The other story is that we always have the uniform boundedness, even when the nonlinear term grows faster than the exponential function. And eventually, you realize that the latter story is true. So the goal of our study is to show the uniform boundedness of global solutions when the space dimension is less than 10 and nonlinear term grows faster than the exponential function. Okay, this is what we would like to show. Okay, of course, the problem in approaching this goal is how we treat nonlinear term, which grows extremely fast. Because we have to treat nonlinear term, which grows faster than the exponential function. So next,
Toru,
let me
sorry, Toru. Hello? Toru, can you hear me?
Yeah, yes.
I want to confirm. So your goal is to prove boundedness of global radial symmetric solution or all solutions.
Okay. In this talk, we focus on radially symmetric solutions,
Okay.
but I want to.
But in the literature, they consider any solution. So there's still an open problem concerning
yes. Some of results only consider radially symmetric solutions.
I see.
Because it's complicated. So some results restrict the solution, so radial solution, but some results deal with any solutions.
Okay.
Basically,
fine.
Okay. So subcritical case is fine, of course. You can treat any solutions, but for the supercritical case, it's very difficult to handle the behavior of solutions. So basically, in the supercritical case, we only deal with radially symmetric solutions.
I see.
Okay.
I see. Thank you.
Yeah, thank you for your question. So,
thank you.
Global radially symmetric.
Yeah, that's fine. I can only, I mean, for general solution, it's very complicated. I can imagine. Okay.
Yes.
Yeah, of course.
So confusing, very confusing.
Yeah.
So I just omit the conditions. Okay. Anyway, in this talk, we assume that the initial condition is always radially symmetric. So all the results are okay in the radial setting. Okay. Thank you. Okay. So let me explain our idea to overcome this problem. Okay, roughly speaking, our idea is to use some good transformation, which in some sense converts an equation with a general nonlinearity into an equation with a specific nonlinearity. Okay, let me explain how to do it. Okay, first, we define a function capital F of u by the integral from u to infinity of 1 over f. So this is always finite because we assume that f is superlinear. Then for solution u of xt of p, our program p, we define a new function v of xt by the logarithm of 1 over capital F of u of xt. I remark that the f of u converges to 0 as u goes to infinity. So this part, okay, this part goes to infinity as u goes to infinity. That means that the new function v diverges to infinity as the original solution diverges. So if you want to prove the uniform boundedness of the solution u, you should prove the uniform boundedness of the new function v. Okay. So the equation for the original solution u is given by the time derivative of u is equal to Laplacian of u plus f of u. And by a simple computation, you easily find that the equation for the new function v is given as follows. The time derivative of v is equal to Laplacian of v plus e to v plus f prime of u, capital F of u minus 1 times gradient of v squared. Okay, the point is that the nonlinear term in this new equation is just exponential function plus some extra term. So if we neglect this extra term in some sense, then the new function v approximately satisfies the equation with the exponential nonlinearity. So we can analyze the behavior of v. Okay, keeping that in mind, so we would like to neglect this extra term. Keeping that in mind, we now assume that the limit of f prime of u times capital F of u as u goes to infinity is equal to 1. We assume this. Then this part gets very small if u is large. And as a result, the new function v approximately satisfies. So of course, we have this gradient term. So if this gradient term is not so big compared with other terms, then this extra term might be negligible. And as a result, the new function approximately satisfies the equation with the exponential nonlinearity in the region where u is very big. Since we know that the equation with exponential nonlinearity, we have uniform boundedness of solution. So v may be uniformly bounded. So this is the procedure strategy to overcome the problem. So we have general nonlinearity. So we convert the equation with general nonlinearity into the equation with the exponential nonlinearity. But where does this transformation comes from? Okay, this transformation is easily derived if you think of an ODE. Okay, let's go back to this simple ODE. If you want to solve this, what you first do is to divide the equation by f of u and then integrate. That means that if you define a new function w by capital F of u, then the capital F of u is defined in this way. So the equation for the new function w is written in this way, which is immediately solved. The point is that this transformation can be done for any f. So of course, if you start from the equation with exponential nonlinearity, you can convert this equation into this simple equation by putting w as in this way. So if nonlinear term is explicitly given in this way, then this integral is explicitly computed in this way. So both equations can be transformed into the same equation. So you can transform the equation for u to the equation for v by the composition of this and this. So this relation can be solved with respect to v in this way. So the transformation from u to v is given by v is equal to log of 1 over w, which is f of u. So this is no other than what I introduced. So this is the transformation for an ODE, but we just perform the same transformation to the PDE. Okay, of course, we have some extra term here, but by assuming this condition, we try to neglect the extra term. Okay, but you may be wondering what functions satisfy this condition. So let me give examples. Okay, let's first consider the case that f is given by u to p with p bigger than 1. In this case, f prime u is p times u to p minus 1, and capital F of u is computed. So this is defined by integral from u to infinity of the multiplicative inverse of u, f. So this is computed as minus p plus 1 over minus p plus 1 times u to minus p plus 1. This is equal to p over p minus 1, which is the Hilda conjugate of p. So the limit is given by the header conjugate of P. Okay, in this case, this limit is bigger than 1. So this condition is not satisfied in this case. But this example tells us that faster growth of the nonlinear term gives a smaller limit. Because if P gets large, then the limit gets small. This means that if the nonlinear term grows much faster, then this limit must be smaller. Okay, let's consider next the case the nonlinear term is given by e to u. In this case, f prime u is of course e to u, and capital F of u is 1 over e to u as computed here. So this limit in this case is 1. Okay, this is obvious because in this case, okay, so v is just u, so there's no change. So the equation for v is same as the equation for u, so this extra term does not appear. Okay, now let's consider nonlinear term which grows faster than the exponential function. For example, we consider the case that e to u to k with k positive. Then by some simple computation, you see that the limit becomes 1. Okay, in this case, limit is 1. Okay, let's consider the nonlinear term which grows much faster. So let's consider e to u. Then the limit is 1. Okay, why not consider e to u? This grows very, very fast. The result is 1. You always have 1. So if you choose nonlinear term which grows very, very fast, the result becomes always 1. Why? Because you can show the following fact. If the limit q, the limit defined in this way, if this limit exists, then this must be bigger than or equal to 1. So as I said, faster growth implies the smaller limit. But the smallest number of the limit is 1. That means that if you choose any nonlinear term which grows very fast, then the limit must be 1. Because the smallest value of the limit is 1. So if you prove the uniform boundedness of global solutions under this condition, then our goal is achieved. Okay. Okay, let me state our main result. Okay, our main result shows that So that's true, which means that if this limit is 1, then we have the uniform boundedness. Okay, we suppose that the space dimension is between 3 and 9, and this limit exists and is equal to 1. Of course, we also assume that the radially symmetricity for the initial function or some non-negativity or something. Okay. Okay, then any global radially symmetric solution u of xt of p is uniformly bounded. So,
but Toru, I have a question here.
Yes.
So I saw your theorem should be any solution is globally global and uniformly bounded. No, it's any global solution.
Yes, if you know that the solution exists globally, then it must be uniformly bounded. Of course, you may have blow-up solution. So,
Really?
yes. So yes.
There can exist blow-up solution here.
Excuse me?
Okay, in your setting, are there blow-up solutions?
Yes, blow-up. Yeah, there exists blow-up solution also.
Okay.
So we have dichotomy. So the solution must be blow up in finite time, or else, global and bounded.
And do you have any criteria for the initial condition such that it's global or it's a blow up? The solution is a blow up or global?
Yes, of course. It depends on nonlinearity, but so the smallness of the initial data will. So if the the initial data is very large, of course, that corresponding solution blows up in finite time. While so on the other hand, if the initial data is very small, so close to 0, and for instance, f of 0 is 0 or something, then there may have some global solutions.
Okay,
there's some criteria.
Thank you.
Okay. And let me mention one remark. Okay, as I showed, okay, if the nonlinear term behaves polynomially, and if f behaves like u to p with p less than the Joseph Lundgren exponent, then we always have the uniform boundedness for global solutions in any dimension. And we also know that if f is given by u to p, then this limit is given by the Hilda conjugate of p. So we can expect that if this limit exists and less than the Hilda conjugate of the Joseph Lundgren exponent, so this means that this in some sense means that f of u behaves like u to p with p less than the Sobolev exponent. This in some sense means this condition. So under this condition, we can expect that the same conclusion as above is true. And indeed, we can show that under this condition that is the same is true. Okay, if f is given by u to p times log of u to r with a constant r, then the limit q is determined only by p, independent of r. Indeed, the limit is given by the Hilda conjugate of p. So this result implies that, so if we take this one as a nonlinear term, then we have the uniform boundedness of global solutions. In the literature, we always have f of u behaves like u to p, but if you multiply log of u in front of u to p, then you have to prove the uniform boundedness by different approach. But this result, in some sense, unifies their results. Okay, in the rest of time, I explain the strategy of proof. I don't want to go into the details, but I just explain the strategy. Okay, let's start from the transformed equation. The transformed equation is given by the time derivative of v is equal to the Laplacian of v plus e to v plus some additional term given by g of v times gradient of v squared. Okay, you don't need to remember this g of v, so extra term, but so by assumption, this converges to 0 as v tends to infinity. So this extra term, in some sense, negligible when v is large. Okay, since we assume that the initial function is radially symmetric, so the transformed function v is also radially symmetric. R is the modulus of x. Okay, we proved the theorem in 3 steps. Okay, in the first step, we construct a singular steady state. Which is denoted by v star of r. So this singular steady state is also radially symmetric. And it is well known that if this extra term is absent, then the equation has an explicit singular steady state, which is given by log of 2 times n minus 2 over r squared. Even if this extra term is added, we still have a singular steady state which behaves like this explicit singular solution near the origin. Okay, this is the first step. So this is shown by perturbation technique for ordinary differential equation because we only deal with radially symmetric solutions. So ODE technique can be applicable. In the second step, we consider the intersection number between the solution V and the singular steady state V star. So we define the intersection number Z of t by the number of R such that V coincides with V star. And in the second step, we show that this intersection number is bounded by some constant independent of the time t. Okay, this fact can be shown easily by using well-known monotonicity property for the intersection number of solutions of parabolic equations. In fact, it is well known that this intersection number is non-increasing in time. This fact immediately implies that this boundedness. Okay, in the final step, we prove the theorem by contradiction. We suppose that V were unbounded global solution. Then we can show that limit superior of z of t as t goes to infinity would diverge. This contradicts the second step. That means that there's no unbounded global solution. Okay, this is the strategy of proof. Okay, finally, let me explain a little bit details of this third step. Okay, let's assume that V is unbounded global solution so that L infinity norm of the solution V diverges along some time sequence Tj. This is the assumption to obtain contradiction. And we introduce some rescaled functions. So we introduce two rescaled functions. One is denoted by Wj of R, which is defined by V of lambda j rho Tj minus log of lambda j squared. And lambda j is given by exponential of minus the L infinity norm of V at Tj over 2. Since we are assuming that this diverges, so this lambda j goes to 0 as j goes to infinity. Okay, by using this lambda j, we define a rescaled function wj in this way. And we also define another rescaled function w star j defined using a singular steady state. In this way. Okay, this type of scaling is often used for the equation with the exponential nonlinearity. So we adopt the same scaling for our transformed equation. Okay, and then we show that both rescaled functions converge to some function w rho and w star rho as j goes to infinity. And also show that these satisfy the same equation. These satisfy the stationary problem of the equation with exponential nonlinearity. And by the definition of Wj, we see that we can show that the limiting function W is bounded at the origin. So this is the bounded solution. On the other hand, Wj star is defined using a singular steady state V star. So the limiting function W star diverges. So this is singular solution of this stationary problem. And it is known that intersection number between this regular solution and this singular solution is infinite. So, okay, so the rescaled functions Wj and Wj star converge to W and W star. And the intersection number between these is infinite. That means that intersection number between Wj and Wj star diverges as j goes to infinity. And this, okay, so Wj and Wj star is defined using U and V star. So this implies that intersection number Z diverges as j goes to infinity. So this is how to prove, okay, this one. Okay, so this contradicts the second step, so we don't have any unbounded global solution. Okay, this is a strategy of proof. Okay, I stop my talk here, so thank you for your kind attention.
Thank you, Toru, for this very clear
Thank you.
and interesting talk. Yeah, very deep talk. Thank you very much.
Oh, I just
Yes.
used 1 hour.
Very nice, very amazing. Yeah, very clear and interesting result. Very good. So any comment, questions, remark from the audience? Please unmute your microphone, ask.
So Toru,
Yes.
can
Hi.
I ask a question?
Yes, of course.
So in the last page, you define Wj.
Mhm.
So in the definition, on the right-hand side of the definition, you have a V of lambda j low and a Tj, right?
Mhm.
So how do you choose Tj?
Tj is okay. Tj appears here, so we suppose that V is unbounded global solution. So we can take some sequence Tj. Oops. We can take some time sequence Tj such that infinity norm of V diverges along this time sequence. So we just use this Tj here.
I see.
So Toru, maybe let me ask you a question. Yes, can you go to your 1, 2, 3, this proof, the strategy of proof up?
Okay.
A topic up. Yeah, here. Okay. So now from your strategy, I can understand why the two-dimensional case is it's bad because there's a mode
Yes.
of some first. And I think the main ingredient of your proof is a zero number, this non-increasing zero number.
Mhm.
But the monotonicity of a zero number holds for all solutions, not just for the radial symmetric solutions, right?
Yes, this but I'm wondering what is the intersection number for non-radial solutions?
I mean, I know there's a zero number by Matano, Fiedler, and Anglin.
Yes.
If you have Gaussian diffusion equation, I mean linear heat equation, single equation, and then you have a zero number. So
zero number.
I am wondering, that your second step and second step in your strategy holds for all solutions, not just for radius symmetric singular steady state.
Yes, yes. So, okay, so you can replace this singular steady state by another
By
solution.
any x, for example,
yes.
not R, but X. This is my point.
So yeah, okay. You can replace this guy with WRT, which is solution of the same equation.
So one dimension. I see. Because you
Yes,
need
yes.
a real
Should
number
be
for
radius.
one dimension. I see. Sorry, I see. Okay, now I don't have a question. Now I understand why. Okay, you really need.
Okay, thanks.
Okay. So the thing is, in order to apply the zero number, you need one dimensionality of your space. So you have to consider
exactly.
radius symmetric solution. I see.
Exactly.
Thank you. But okay, this is also related to my next question, because I mean, if I want to prove a solution is uniformly bounded, the most natural way is I try to construct another comparison solution which is bounded but higher than me, and the zero number it's a way and it's very strong. Have you ever tried to somehow find like a upper solution which is uniformly bounded?
Yes. Comparison principle is one of the way to prove the uniformly boundedness, but okay. So what we assume is only so we only assume that the solution exists globally. There's no information other than the global existence. So it's
you collect
not
your
easy
proof.
to,
It's the only way. It's the only way. Okay.
Yeah, I think it's very hard to construct some upper solution. Yes, I have to try, but I think it's not so easy to
somehow if you want to prove there is a blow up solution, that you construct a lower bound solution and which blows up in finite time, that they always prove into. Somehow I have a feeling that the lower bound solution is easier. The construction of a lower bound solution is easier than upper bound solution somehow.
Yes, in some sense, yes.
I don't know why. Yeah, to be honest, but yeah. Okay. Good. So, other question, comments?
So I have one more question. So do you also consider doing some symmetrization of the solution as well as the domain, so that you get a radial symmetric problem? Would that problem give us some help to study this kind of phenomena?
Yes. I'm not sure that it's applicable or not, but yes, we may. Yeah, we should try to do it. Yes. Yeah, thank you for your advice.
Maybe very complicated. Yeah.
Yes. Yeah, I think it's very hard to compute everything, but yes. Thank you. But I'm not sure it's applicable or not.
Okay, thank you very much.
Thank you.
Yeah, and there's okay, I have another remark maybe related to Professor Chen's question. So after this radially symmetric solution, you can consider like how to say, maybe spiral wave solution, right? You have a UR times exponential I omega theta. Theta is this angle of your disk or of your n-dimensional sphere. So you have additional one freedom of frequency. Then it's not ODE, it's still PD. It's OD in the end, to be honest. If you substitute this answer, you still get OD. But you have an additional term regarding this omega, this radial gradient, something like that. And maybe your technique still works in this sense.
Okay.
Yeah.
Yeah, thank you. Yeah.
So you can Google that spiral wave or, because your radius
I understand what you mean.
Yes, your radial symmetric solution is a so-called target pattern, or target wave.
Hmm?
Good.
Okay, I don't know the name, but I understand what you mean.
Yes, yes.
Mhm.
Good. So, other questions? Comments? Okay. If this is not the case, then let's thank our speaker, Professor Toru Kan, again.
Thank you.
Thank you.
Thank you so
Thank you
much.
so much.
Thank you. So, okay.